Hello, today we're going to build some computer vision models using point-and-click custom steps in SAS Studio Flows. The computer vision custom steps can be downloaded from Git, and after downloading those custom steps, you need to store the custom steps on your system under SAS Content and Public. I like to create a folder called Custom Steps, and this is where I place my computer vision custom steps. Placing those steps here will surface them under the shared folder on the Steps pane. You also have SAS steps. We'll be using some of these today as well. Let's start with a new and select Flow. From the flow, I'm going to select the shared to access the shared custom steps. We need to pull in some managed connection nodes. I'm going to pull in two of these nodes. The first node, I'm going to select the desired task to be to terminate a CAS session. I do this just out of extra precaution to make sure that no other CAS sessions are hanging. Next, I create a new CAS session. I want these nodes to run in order, so I'm going to turn on the far right, submission order. This creates swim lanes. Now we're ready to get started. The first model that we're going to build, or computer vision analysis, is for object detection. So I need to pull in the Create Object Detection Table node. I left-click, drag this in, and this creates a third swim lane. When I left-click on the Create Object Detection Table node, the options surface below. You can see that I have a parent directory containing images and annotations. This is where my data is stored. So I need to left-click on the Select a Folder button and navigate to my data. I'll do that now. I'm going to select Dr. Taco XMLs. This contains images and XML files, and I'm going to select OK. We can choose to resize the images if we'd like. We have several options for object detection: 224, 416, 640, or 1280. Most object detection models I'll run at 640. If I have situations with really granular objects, it may be advantageous to run at 1280 by 1280, but you would want to use a ShuffleNet style model if you're doing that. For today's demonstration, I'm going to stay with a 416 by 416. Sometimes you'll have a lot of data, and loading the data and the XMLs and creating the annotations, it can take some time. So we offer an extra option called Save Object Detection Table Locally. So when you run this node, let's say if it takes several hours, you actually have the option to create a SAS HDAT, which next time you load it up would be very fast. Given that the data is not too large, I'm going to select No for today. Next, I need to add a table node to this swim lane 3. I'm going to left click on swim lane 3. I'm going to go up to the Add option, and I'm going to select Table to add a table to swim lane 3. I'm going to create a connection. Note that currently, for all computer vision SAS Studio Flows, the library must be set to CAS user. We'll change this in the future, but currently, make sure that the library is set to CAS user. The table, you can call this whatever you want. So I'm going to call this Image Table. So we load up some images and create as well as the XMLs, and we create the object detection SAS HDAT. Pass that forward. Next, we're going to train some models. To do this, I pull in the computer vision model development. We're currently on version 6, but we'll soon be on version 7, which will have some nice additional features. Two important options that need to be specified when you're creating computer vision models in the SAS Studio Custom Step Flows is 1, your project folder path, and 2, a folder where the models reside. The project folder is usually a folder that you create on your system where you're going to store the important files that are generated from this process. These files can include auto-tuning tables, as well as the model architecture table, the weights, and the weight attributes. I'm going to select a folder, and I'm going to select the original ShuffleNet. We're going to train the original ShuffleNet on 416 by 416. So I'm going to select OK. This second folder contains the model SAS HDAT, the model table, SAS HDAT, the model weights in SAS HDAT format, as well as the model attributes, also in SAS HDAT format. So if I select a folder, I can navigate in my system to the location of my models. Once I select that folder, I'm ready to go. Before I move on, let me show you in the system what this folder contains. So I'm going to navigate up to Explorer, and I'm going to navigate to that same location. Here you can see the SAS HDATs for the model architecture, the weights, and the weight attributes. The A stores do not need to be included. Just the model table, the weights and the weight attributes. Okay, so now we're ready to continue forward. Let's go down to the modeling task. There are several selections for task: object detection, classification, regression, or multitask. Right now we're going to focus on object detection, but we'll cover some of these others later. I left-click on object detection. If you have GPUs on your system, which is highly recommended for computer vision, you can select GPUs equals true. Next, we have to specify the column in our data that contains our image. By default, it's underscore image underscore. For the image size, I'm going to leave this at 416 by 416. Built underneath the code here in the model training table is a process image action that will resize images to the selected size here. So if you don't resize to the appropriate size in the create object detection table node, you can tackle that here in the model development node. For number of classes in the object detection table, currently we're just detecting one: my dog, Dr. Tucker, running around on the beach. So I'll leave that at 1. We specify the color, the number of channels in the image, whether it's color or grayscale. We can apply photomorphic and geomorphic transformations on the fly randomly to every mini batch that comes in. This helps with generalization, so I'm going to apply this. This is a drone flying around on the beach looking at my dog, so I'm going to apply both horizontal and vertical flips because that logically makes sense. This is an object detection task, so we need to generate some anchor boxes. Anchor boxes should really be geared for your data that you're using. So in this case, I'm going to generate some anchor boxes on the fly for the data that's being fed in. Behind the scenes, procK+ is being used. You get to choose the optimization method for the optimal number of anchor boxes. I'm going to stick with the first maximum with standard deviation. Last, under General Setup, we specify the percentage of cases to be held out in our validation data. I'm going to hold out 20% of my data in my validation. Next, I'm going to select the modeling options, and under modeling options, you can see I have auto tuning, model specifications, and final model training. We're going to come back to final model training. Let's start with auto tuning. I would like to auto tune this model to help me get a good model off the bat. So I'm going to answer this question with a yes. After answering this question with a yes, I need to specify a SAS HDAT name. Now, notice that another question appears below. Do you want to leverage a previous search? I'm going to actually switch this to yes. It's common in computer vision modeling that a single evaluation, looking at the performance of a model, training it for just say 20 epochs, could very well take 2 to 3 hours, depending on your data and model that you're looking at. So it's common practice for us to need to build on our previous results. Maybe run this process overnight or over the weekend, look at the results, and if they're not good enough, continue forward without losing our previous work. So I'm going to select yes, because I'm going to do that now. I've actually done some training on this data previously. So I'm going to feed in as my starting table this AutoTune V2. And for my current table, I'm going to switch this to AutoTune V3. Again, AutoTune V2 is a SAS HDAT that is stored in my project folder. That was created under General Setup. So clearly, I've already done some training. I already have another project that's pointing to this folder where I've done training. Back to modeling options. And I've done, it looks like, 2 evaluations, or at least two iterations, 2 versions of this. So now I'm on version 3. If you select that you do want to leverage a previous search, you have the option to seed your current search. This is a demo and I want to move fast, so I'm actually going to change this to 2. That is, I'm going to take the top 2 performers from my previous search history and I'm going to feed them into the current search history. Next, we have our normal auto-tuning search options. Changing random seeds. It's always a good idea to change a random seed if you're building on a previous run, and you'll see notes in the system that details that important information. For population, I'm going to stick with 2. Again, I want to train this fast. Generations, I'm going to select 1. So the 2 that we're going to train are going to be the 2 best performers from my previous search. If you know or if you're familiar with the algorithm behind the scenes, it's evolutionary algorithm guiding local search. So we have a greedy algorithm. I'm going to set this to 0. And number of evaluations or epochs per evaluation, I'm going to set this to 20. Next, I specify the maximum number of seconds for the search. When I'm running this in practice, I'll usually actually do the math. 60 seconds times 60 minutes times the number of hours that I'm going to be training my model. In this example, I'm going to set it to 900 seconds, so it's just 15 minutes at most. And lastly, I can select whether or not I'd like to save a PDF. This is actually an HTML that'll be saved in the project folder. This is useful if you're training, let's say over the weekend, and you're late into the office and SAS Studio session closes on you. And you're like, oh no, I missed the results. Don't worry, the results is saved in an HTML in your project folder. I think you're beginning to understand why this project folder is important. Lots of important information is stored there. So we've concluded the auto-tuning section, so I'm going to minimize it, and I'm going to open up the model specifications. We can specify the number of threads. And next, because this is an object detection task, we actually have options that are specific for object detection. If we were modeling image classification, multitask regression, we would not have these same options. These are specific to object detection. So these are the scalars for the multi-loss error function used in object detection. I don't know the appropriate value. This is the default and what was used in the paper, but maybe there's a better value. So I'm going to select this checkbox where you can see a lower and upper bound surface. So I'm going to search an appropriate value between these bounds. And I'm going to repeat this process for many of these other object scalars and the multi-loss error function. Now notice that there is a wait for classification error. Well, I only have one class in my data, so I don't need to search this. Actually, I don't even need this value. If I set this as a 0, this will simplify the model's error function, making the model better at predicting the location of Dr. Taco. So I'm going to set that to 0. I'm going to search the detection threshold, the IOU threshold, and the training IOU threshold. I'm going to search all of these options. Next, I can select the model backbone. Currently, we have ResNet TinyYOLO v2, which is just a VGG16 style backbone, ShuffleNet v2, a more complicated ShuffleNet v2, and a very complicated version of ShuffleNet v2. We've actually tested the very complicated version of ShuffleNet v2 in our ESP engine, and our ESP engine, which is incredibly powerful, can run the most complicated version on 640 by 640 at frames of about 16 frames per second. I'm going to stick with ShuffleNet v2, but notice you could also auto-tune the backbones. So if you don't know which backbone to select, you could auto-tune across all backbones. In a forthcoming release, we're actually going to let you select which models you'd like to consider if you select the auto-tuning option. Currently, I'm going to stick with ShuffleNet v2. Next, you can pick the size of the convolutional filter in the first convolutional layer. I don't know the size, so I'm actually going to search that. For a nonlinear activation function, you can select a nonlinear activation function, or you can choose to search it. I'm going to stick with Leaky ReLU because in my experience that works pretty well with these object detection models. I'm going to search the learning rate, the difference between beta 1 and beta 2. For the mini batch, I know that ShuffleNet's first layer has 24 filters, so I'm going to set the mini batch to 24. I'm going to search the step size, the gamma value, and a few of these others, gradient clipping, and I won't worry about my regularizations just yet. Below the regularizations, you also have a choice to either set a dropout per layer or block, or search it if you'd like. I'm not going to apply any dropout in this iteration. Next, we have final model training. Auto-tuning is going to search many different model combinations and variations. So in this case, it's just looking at ShuffleNet v2. But if it were looking at other backbones, it'd be pulling in different model backbones and modifying the architecture, looking at different filter sizes, nonlinear activation functions, as well as changing the hyperparameters. In some instances, we allow you to actually insert projection layers. We'll talk about that when we get to multitask. After auto-tuning runs, the best performing model architecture, the best performing weights and weight attributes, and an updated learning rate are all passed forward for final model training. That is, the final model picks up where the best performer from auto-tuning left off. So if we've trained or evaluated our models in auto-tuning for 20 epochs, we are starting at 20 epochs of training, and then we're going to train for another 50 epochs. I'm not going to set this to 50 epochs. I'll set this to something like 35. Now notice that there's an output table port coming out of this computer vision model development node. Let's add another table to the flow. And remember, the library has to be set to CAS user. For the table name, I'm going to call this model info. The information coming out of this table is not your scored computer vision data or your inferenced images. It is instead important information about this model, including where the model sits, that is in the project folder, the name of the model, so you're pulling the appropriate model architecture, the name of the weights, and other information like image size, and so forth. This information is then passed to the next node, which would be your computer vision model deployment node. You could also use model scoring if you'd like. In this example, I'm going to use model deployment. So I'm going to create a connection between the model deployment node and the model info node. Now, if you're not using event stream processing, it's likely that you're going to deploy the model maybe outside of SAS using ONNX. In this example, I am going to deploy this model in SAS event stream processing. So I'm going to answer the question with a yes, and then I have to specify the number of objects that I would like to detect. Number of objects is different from number of classes. If you're detecting people, you could have one class, but you could have many people in an image, let's say 200. So you may want to set this value to 200. In this case, it's just my dog running around on the beach, Dr. Taco. So yes, he is one class. He is also just one object. There are not two of him, just one of him. But remember, number of objects is different from number of classes. And finally, we need to select a folder to save the model. I'm going to save this in my project folder, titled Original ShuffleNet with 416 by 416. Next, we need to add another table object to this flow. And as always, set the library to be CAS user. And I'm going to call this table deploy info for deploy information. Just like with the model info table, this node table here is going to contain important information pertaining to the ESP deployment. So I'm going to pull in the ESP deployment package node, and I'm going to create a connection between model deployment and the ESP package deployment. In the ESP deployment package creation node, we first need to select a location to store the ESP zip file. This zip file is going to contain important information such as the model HDAT, an XML file which has been modified or adjusted for the model and data at hand, as well as a test file if you so choose to include one. I'm going to include a test file. So I'm going to select, would you like to include a video file in the ESP package? I'm going to select yes, and I'm going to navigate to the location of the video file. I select the file and select OK. And we also have the choice to name the zip file. I'm going to call this Dr. Taco Shuffle 416. Now we're ready to run our flow. Let's kick it off and see what happens. Now that the flow has completed its execution, we can examine the results. I'm going to surface the results in a new window just so we have more room to examine them. We can see a sample of images that were uploaded by the Create Object Detection Table node, as well as overlaid labels for those images. Next, we get into the Model Development node, where we use proc kclus to determine the optimal number of anchor boxes. Here, it appears that kclus is recommending 2 anchor boxes of these sizes. We continue to scroll down and we can see the results for our auto-tuning. So notice that in the evaluation time, we have 3 evaluations that occurred for the models that were trained. Remember, 2 of these models came from a previous run. All of the rows, which represent models that were evaluated, that have an evaluation time of 0 came from a previous search. On the left-hand side, we have our objective function value. So lower is better. This objective function is a two-part objective function. One part is intersection over union on the holdout data, and the other part is a normalized error function on the holdout data. Notice that the values in this table are human readable. So for backbone used, you can see it says ShuffleNet v2. For activation function, we have leaky ReLU. For first convo filter size, we have 7x7, 5x5, and so forth. As I scroll through the table, I can see the results for the top 3 performers, which all 3 happen to be trained in this iteration. If I scroll down to the bottom, this top performer here is fed in and used in the final model training, which we see here. Blue is the fit error, and yellow is the validation. It appears that this model is actually doing better on the validation than it is on the training, so we have perhaps more room to fit the model to the data. And of course, lastly, we get to see the predictions overlaid on the images and the holdout data. And this is just a sampling determined, which is a percentage determined by the value selected in the model training node. It appears this model is doing very well. And I may have not mentioned that earlier, but under the final model training, you have percentage of holdout data to view, which is what we were looking at, 1%. So next we have the CV model deployment that created an A-store, as well as this CV ESP deployment. These values should be stored in the project folder, so let's go check them out. Here we have the zip file, the Dr. Taco ShuffleNet 416 zip file. I'm going to download the zip file so we can view its contents. It'll take a while because the video in this file is rather large. It looks like the download has complete. Let's open the zip file and view the contents. We have the Analytics A-store, the Model XML, and the test file. Now we're ready for deployment and testing in SAS Event Stream Processing.